In lesson 6.5, we're going to look at more to do with exponential relations. Remember, growth means an exponential relation which is increasing as time goes by, or as you read a graph from left to right. Decay means that something is decreasing, or if you're looking at a graph, it's going downwards from left to right. We've already seen in our last lesson that exponential relations can be represented with this equation, y equals a times b to the x. A is the initial value, b is the base, and it determines how fast values grow or decay. X is the exponent, it's the number of times that the base has been applied. Again, think about something like, for example, a simple exponential equation, y equals 2 to the 3. 2 to the 3 simply means that you're going to multiply 2 times itself 3 times. So that's what they mean by the number of times that the base has been applied. It's the number of times you multiply the base by itself, if you're working it out. Remember, b is a growth factor if b is greater than 1. Right? In other words, we've seen this before. This is the greater than sign. And if it's between 0 and 1, then it's going to be decay. Many situations can be modeled with an exponential relation that represents exponential growth or exponential decay. Some examples are population growth. That seems to grow exponentially, whether it's people or bacteria or animals. They grow generally following an exponential pattern. Investments can grow. Compound interest grows using an exponential pattern. Depreciation of values, such as cars. You buy a car and the money, year by year it goes down, but it doesn't go down in a linear rate. Usually it drops its most value at the beginning and starts to flatten out later. So that's exponential decay. And half-life of scientific materials. So here are just some examples we can look at to drive this idea home. Example 1. In a national park, a wolf population increased by a growth factor of 1.078 per year over a 10-year period beginning in 1997. So the formula here modeled the wolf population. So P for population equals 124 times 1.078, which we've already seen, right? That's the growth factor, to the exponent t, where t is the number of years that have gone by. What does the 124 and the 1.078 represent in this formula? So this is in the A spot. And by the A spot, I mean up here, A, right? That's actually our initial value. So the initial value, in this case, the initial number of wolves, starting amount of wolves, or to put it in a more usual way we say it is, the number of wolves that there were when they started was 124. And then this is our growth rate. I know it's growth because 1.078 is greater than 1. It's not a lot bigger than 1, but it's greater than 1. So that means that the number of wolves is going to go up over time. What was the wolf population in 1997? Well, it was 124. It's the starting amount. Starting amount, because we were starting in 1997, right? 1997 was when this one started. Before I even move on, we can still use the equation to help us work this out. 124 times 1.078 to the exponent t, where t is the number of years. So if we started in 1997, and we want to know the amount in 1997, then how many years have gone past? Well, the answer is 0 years have gone past. Remember, anything to the exponent 0, though, equals 1. So it's 124 times 1. And so that's another way to get that 124 wolves. What was the wolf population in 2007? Well, now 10 years have gone past, so that means that t equals 10. So, and I guess I shouldn't have used y up above, I should have used p, shouldn't I? So p equals 124 times 1.078 to the exponent 10. And when I put that in my calculator, it works out to be approximately 263 wolves. So you can see that the population of wolves has gone from 124 in 1997 to 263 in 2007. So that's growth, and that's the idea behind this. The initial population in a bacterial culture is 500, and the population grows at a fixed rate. The table shows the population for every hour for 6 hours. Calculate the ratio of successive y values, then use it to write the equation. All right, so remember, for an exponential relationship, we have a common ratio. So it's not first differences, it's the ratio. And the ratio, it comes from dividing the second number in it. If I take two of them, so let me back up for a second. Say I take these two rows here, all right? If I divide the second number by the first number, that'll give me the ratio that's going on here. So if I do 550, stick a 5 there, divided by 500, second number divided by the first, equals approximately 1.1. And then if I do the second number here divided by the first one, if I in these two rows, then I have 605 divided by 550, which also equals approximately 1.1. And if I keep doing this, 666 divided by 605, I'm going to keep getting 1.1 over and over again. So that's my common ratio. Okay, so my common ratio is 1.1. That's also going to be the b value of my equation. So let's go back to the equation. Y equals a, starting amount, times b to the x. That's the form of the formula. Let's change the variables a bit. Let's say h for time, because, well, that's already there instead of x. And let's call the population p. So if we do that, then the form of the equation is now going to be p equals a times b to the h. But we still need to know what a and b are. So I already said the common ratio, b, was 1.1. Let's leave a space for a. So we got 1.1 to the h. And remember, a is our starting value. Well, what's our starting value? Well, logically, our starting value is the value at time 0, right? So in other words, the population was 500 at time 0. That was also in the question, by the way. You can see it up here. But even if it wasn't given in the question, we could have gotten it from the table. So there is our equation. Now that we've got this equation, let's put a nice little box around it. Now that we've got this equation, we can use it to find the population of bacteria after 12 hours and after 24 hours. For 12 hours, then I would just put 12 in for h. So population equals 500 times 1.1 to the 12, which equals 1569. After 24 hours, then p is going to equal 500 times 1.1 to the 24. So that's a full day. Now it's up to 4925. How long will it take for the population to reach 10,000? Right now, it's, after 24 hours, we saw that it was about 5,000. So maybe it'll take another day to get to that amount. But I think that we can probably find that being exponential, it's going to grow a little bit faster than that. But the way we can work it out is we can put that value in for p, into our equation. And now we have to solve it for h. Now solving for h is a little bit harder because it's the exponent, right? But what we can do is we can start by dividing each side by the a value, by 500, because then it'll cancel that out there, and I'll be left with, let's see, divide that, I guess I'm left with 20. So I can simplify things a bit. 20 equals 1.1 to the h. To find out what h is, though, really what I need to do is use trial and error. In other words, try plugging different numbers in until you get 20. So let's go to my calculator. If I have 1.1 to the exponent, what? We saw that 24 was not high enough before. So 24 only gave us about half what we wanted. I'm trying to get it to be 20 right now. 24 gives us 9.8. No big surprise there. So what if I double that? 1.1 to the exponent 48. Well, that's way too much. I want it to equal 20. So again, the exponential nature of this causes things to grow faster as time goes on. So we don't need to go anywhere near as high as 48. Why don't we try something closer to 24? So why don't I try 30 in this case? Okay, that's getting closer to 20. I need to go a bit higher, though, right? 1.1 to the exponent 32. Now I've gone a bit too high. Let's try to see if 31's a bit closer. 31's a bit low, but it seems to be about the closest. Somewhere between 31 and 32. Well, what does all that mean? Well, what it means is that after 31 to 32 hours, the population will be 100,000 bacteria. Whoops. Remember, the reason why I was getting it to be close to 20 instead of 100,000 is just because I did a little bit of simplification up here. I started out with 100,000, but divided each side by 500 to make the numbers a little smaller, and that's where the 20 came from. If I were to put that 31 or 32 back into the original equation, though, P equals 500 times, let's try 1.1. Let's try somewhere between 31 and 32. Let's try 31.5. See what we get. Not now. 500 times 1.1 to the exponent 31.5. And I got, I guess it wasn't 100,000, it was 10,000. But anyway, I got 10,065. So very close to what we were looking for.